Let me show you how to be a good Bayesian.
Today, I am thrilled to host Nathaniel Forde, a staff data scientist at Personio, where he works on people analytics for one of the leading HR intelligence platforms. With more than a decade of experience spanning insurance, gaming, and e-commerce, Nathaniel brings a wealth of knowledge to the table. He's also an active contributor to the PyMC ecosystem, with a particular focus on causal inference. In this episode, Nathaniel takes us on a deep dive into the world of structural equation modeling, or SEM, and confirmatory factor analysis, or CFA. We explore the advantages of Bayesian approaches in handling these models, from greater flexibility to enhanced model validation through sensitivity analysis. Whether you're curious about fitting complex models to real-world data, the intersection of SEM and causal inference, or the growing role of Bayesian methods in industry applications, this conversation offers insights for both beginners and seasoned practitioners. This is Learning Bayesian Statistics, episode 121, recorded October 11, 2024.
Let me show you how to be a good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. What's a Bayesian? It's someone who cares about evidence.
Welcome to Learning Bayesian Statistics, a podcast about Bayesian inference, the methods, the projects, and the people who make it possible. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. For any info about the show, learnbayesstats.com is la place to be. Show notes, becoming a corporate sponsor, unlocking Bayesian merch, supporting the show on Patreon, everything is in there. That's learnbayesstats.com. If you're interested in one-on-one mentorship, online courses, or statistical consulting, feel free to reach out and book a call at topmate.io/Alex_Andorra. See you around, folks, and best Bayesian wishes to you all. And if today's discussion sparked ideas for your business, well, our team at PyMC Labs can help bring them to life. Check us out at pymc-labs.com.
And before we start the show, I wanted to particularly warm our new members in our small Bayesian family on Patreon. Thank you so much to the mysterious Undrilled 9830 and to Alex for joining the full posterity or higher on Patreon. I hope that you will enjoy your merch. And Alex, I want to tell you that not only, I love your first name, of course, but also you joined on November 13, which is my birthday, so thank you so much for the birthday present, Alex. Can't wait to see you guys in the Slack channel. And now, let's hear from Nathaniel. Nathaniel Forde, welcome to Learning Bayesian Statistics.
Thanks for having me, Alex.
Yeah, thanks for taking the time. It's always a pleasure to have you on the show, even though it's the first time. On the main format, but you've already been on the show actually to do a modeling webinar. I think it's the first time that happens. So you first appeared doing a great modeling webinar about Bayesian non-parametric causal inference. You demoed how to do that with PyMC, and I think there is even some BART model in there. So it's a very in-depth tutorial that I definitely recommend people interested in to check out. I will add it to the show notes, of course, as well as the video of the webinar, because I encourage people to follow along the video because you're demoing that live with the tutorial, and there are also some of the live questions. And you're actually a specialist of these in-depth guides and tutorials, mainly about causal inference because it's one of your favorite topics. And that's also why I thought it was interesting to have you on the show today, because you have a new tutorial out on the PyMC website. And that time I was thinking, okay, now it's time to have you on the show and also talk about what you do and your background. So thanks a lot for taking the time. And well, let's start as I always do. Can you tell us what you're doing nowadays and how you ended up working on this?
Yeah, certainly. So I'm a data scientist for Personio at the moment. It's a sort of HR intelligence platform, like a kind of one-stop shop for all your sort of HR workflows and sort of insights. I've been working there for about 3 years. And I've been working in data science or data science adjacent roles in industry for about 10 years. So yeah, I think I got a little bit lucky with my first job in industry, which kind of set me up well to sort of move into data science more generally, which I can speak to as well. Like the so I kind of graduated from university into the teeth of the global financial crisis. So like I was took the first job I could get, but was fortunate because I got a job with Marsh & McLennan, which is a huge insurance kind of company. They've got Oliver Wyman, Guy Carpenter, Marsh underneath them, and they were spinning up a innovation center in Dublin. And my first job was working for Marsh on their new data quality function, which was kind of a neat first job for like anyone who was data curious, because the sort of flow of that job was like every quarter you'd get a new data set from Marsh and you'd have to try and evaluate it for data quality, missing data, poor sort of data entry, this kind of thing. You basically highlighted like the risks of poor data quality for all the use cases that Marsh had in the company. So it was a good first training ground for, say, a budding data scientist, we'll say.
Yeah, for sure. And how did you end up then in the? I can see causal inference coming in here, but how did Bayes come up? Do you remember when you were first introduced to Bayesian stats?
Yeah, I was thinking about this the other day. So I think I had to be introduced to Bayesian stats twice, and the first time it didn't really take for me. So like in university, I did philosophy and kind of went into mathematical logic after that, and as a sort of tangent from studying mathematical logic, I was working on different logics of dependence, so like justification logics and dependent structures and independent structures. And I kind of came across Judea Pearl's work on independent structures and the graph relationships between sort of probabilistic independence and graph like directed acyclic graphs. And that sort of backed me into sort of thinking about the sort of conditional probabilities and Bayesian probabilities from I even worked on trying to replicate Pearl's completeness proof of like the relationships between probabilistic sort of algebra and the independence relationships on those graphs. So like from a sort of highly theoretical perspective, I kind of came across Bayes and it didn't stick. Like it didn't resonate with me. I kind of worked through some of the mathematics, but I didn't get it, I don't think. And it really took exposure in industry. In my second job, I think I worked in Guy Carpenter for about a year, and it was kind of a nice role because I worked with the sort of catastrophic risk modelers. So they were building risk models for portfolios of property that were at risk from some natural disasters like earthquakes or floods or fires. And they would try and sort of simulate over sort of multiple, basically Monte Carlo, MMC kind of modeling to estimate the risk to each sort of portfolio of properties. And like seeing that application was sort of my first sort of exposure to this is a practical tool that it can be very useful and very informative for making massively important decisions about like the nature of disaster, catastrophic risk. Like countries were buying insurance contracts from, say, Guy Carpenter. Like Mexico would insure itself versus earthquake risk based on like kind of simulation data. So that was the second time, and it really stuck with me that was a sort of practical tool, and it kind of connected the dots in my head a little bit with the theoretical background and the practicalities. And then I just kind of started looking into where should I learn this, and found PyMC and the sort of welcoming kind of community there. And well, you know,
the rest is history.
Yeah.
So actually today I invited you because you have this new tutorial about structural equation modeling, confirmatory factor analysis. So that's already 2 acronyms, SEM and CFA, that we should definitely introduce. So could you start by explaining the basics of SEM and CFA for listeners who might be new to these concepts?
Yeah. So I think that maybe the way I kind of came into trying to understand confirmatory factor analysis was probably initially the scikit-learn factor analysis methods. So the presentation there in sort of a typical sort of machine learning workflow for factor analysis is to think of it as a dimensional reduction technique. So you have like this wide array of features, your X matrix and your prediction problem or whatever, and you think that there's a bunch of them that are kind of related, and you want to sort of zip them up into one feature that simplifies your modeling workflow. So like you take these related features, push them through this factor analysis routine, and it spits out like maybe 1 factor or 2 factors, depending on what you're aiming at. But it reduces the complexity of your data set by kind of not exactly aggregating up multiple features, but creating new features from existing features. So that was my first sort of exposure to factor analysis. Confirmatory factor analysis is more common, less not in machine learning workflows, but more common in like psychometrics and sort of social sciences, like educational sciences, sort of learning development sciences, where the factor itself, the thing you wrap up all your features into, is of independent interest. So you might have this kind of construct or notion of, say, mathematical aptitude, which is not itself directly measurable, but you have a bunch of measures that seem related to it, right? Like, or should be informed by it. So like historic test results on like, say, your junior cycle math exams and your other cycle math exams, and like how do they all kind of collectively inform a view of your individual mathematical aptitude. So a confirmatory factor analysis model is interested in these abstract constructs, and you might gather a wide data set, and you want to sort of reduce it in terms of complexity, but also see which are good measures for which of these latent factors exist. So this is often the case, and so so basically it's a dimensional reduction technique, but the things that you're reducing to, these multiple indicator variables, are of independent interest themselves. So you might want to try and measure this latent construct of mathematical aptitude and see if that itself is predictive of future math scores, for instance. So that's kind of factor analysis, and the confirmatory part is you're making a statement by building this model that these indicator variables, like say your historic math scores, load onto this aptitude factor well, and they make sense collectively as indicators for this abstract notion of aptitude. So, and what you're trying to do when you fit a confirmatory factor analysis is make sure that the specified relationships between these abstract constructs and your variables that you define in your modeling architecture make sense and can recover aspects of the observed relationships in your data matrix. And primarily, you're interested in recovering the correlations and covariance structures between your observed variables. And so as you build out that architecture of the confirmatory relationships, you then evaluate the success of your factor model by seeing how well it can recover the covariance structure in your observed data.
Okay, so that means, does that mean CFA has like more structure in it because you assume the model has a structure kind almost like a DAG?
Yes. You're like imagine you have a data matrix with 6 variables. You say that the first 3 variables are related to life satisfaction in the case that I was looking at, and the second 3 variables are related to measures of parental support. So you want to sort of abstract across those 6 measures to have like one score for each individual on how well supported they were by their parents, and another score for how well they report life satisfaction scores, for instance. But you are imposing that structure. Like you're imposing that structure to say, these 3 variables load on this factor, these 3 variables load on this factor, and you're trying to confirm that structural specification by seeing how well that model can then reproduce the observed covariance structures between the 6 indicator metrics that you actually have in your data set.
And the difference with classic factor analysis here in that example, for instance, would be that you would not be telling the model that the first 3 factors relate to life satisfaction and the 3 last factors relate to parenting. You would just put everything in the same model and just see if the model picks that up itself.
Machine learning approaches are kind of often less theory driven and more sort of, does it perform better predictively on the outcome I care about? Confirmatory factor analysis is sort of inherently theory driven. You are trying to describe what you believe to be the operating theory that drives these outcomes.
Yeah.
And by evaluating the confirmatory, or by trying to confirm the factor analysis structure that you've specified in your model, you're in some sense trying to validate a theory of what drives these outcomes of interest.
Okay, yeah. So I can clearly see the link then with DAGs and causal inference for sure. Yeah.
And so, so that's already seemingly kind of complicated enough, or at least hard to explain on a podcast setting. And then structural equation modeling on top of that is a way in some sense to add yet more structure to the theory that you wish to confirm. So you now have all your measures for your indicator variables, so your 3 for life satisfaction and 3 for parental support. But now you want to say that of the 2 latent constructs that you've just defined, that there's a regression relationship between those 2 constructs, for instance. And then we say we try to predict life satisfaction from parental support. And structural equation modeling is used across a bunch of diverse fields and means maybe subtly different things in each, but inherently it's just about adding more explicit structure to the relationships in your big multivariate joint distribution. And you can be quite explicit in how you structure those relationships or those dependency chains. You can have chains of regressions or chains of sort of functional relationships between your indicator variables, but also the latent constructs that you sort of derive via your measurement model, the factor analysis structure that you have baked into your structural equation model.
Okay, yeah, I see. So actually for people interested in more about structural equation modeling, causal inference and psychometrics, I recommend listening to episode 102 with Ed Markle. I linked to that in the show notes because that's where Ed is doing psychometrics. So that's really, it seems to be used a lot, SEM in psychometrics. So for people interested in that, definitely recommend that one. Today we're gonna focus on your tutorial about CFA and SEM, Nate. Nathaniel. I know you prefer going by that. And actually, I'm curious, what were the main goals of this tutorial and what prompted you to explore this area?
Yeah, so what prompted me to explore, so to be clear, none of the data we used in that tutorial is Personio's data, but work in Personio, so it's a HR platform, an intelligence platform, and like one of the sort of primary ways in which HR departments attempt to gauge their on the employee base in any company is to run sort of regular surveys of different stripes. And sort of the main or canonical survey that gets run across most industries is like an engagement survey. So where you're trying to build a model or understand what drives employee engagement or satisfaction in some sense or other. And those surveys can be quite dense. Like there's many questions across sort of different themes about your sort of work-life balance or your working conditions or your working autonomy. And so it's kind of a psychometric adjacent question. You're trying to figure out like what is it that what metrics load on aspects of employee happiness, and how does that happiness drive their engagement, and how does ultimately questions of like how does engagement drive productivity and the business's bottom line. And it's a problem that is just well suited to structural equation modeling. And I didn't know enough about structural equation modeling to be comfortable applying it sort of out of the box tools. So I wanted to sort of dive into the modeling framework, understand it better, and kind of build it in a framework I know well, which is PyMC. And like the beautiful thing about probabilistic programming languages and PyMC as well is that it offers you this language or freedom to express those complicated modeling structures in a way that A, I'm familiar with, but B, is also very intuitive and powerful given the Bayesian setting.
I see. Yeah. So that was a way for you to learn in an open garage way, in a way. And so, what are some of the key challenges actually that you experienced in applying SEM and CFA?
So so there's a lot of, like, I think you mentioned Blavan is a package that's being developed for Bayesian structural equation modeling.
Exactly, by Ed Merkel. Yep.
Exactly, and that is sort of an augmentation of the more traditional Lavan package, which is also used to estimate structural equation models. Lavan tries to fit these models in a more say classical way or frequentist way. So often fits these models with maximum likelihood sort of methods. And so I've tried to use those models, and because there's a lot of tooling around Lavan, which makes it easier to interpret these models, and it's a powerful package in its own right. But these models are sort of inherently quite complex. Like, you're building rich structural relationships with many parameters in a lot of cases across complex and possibly not well understood relationships in this sort of multivariate survey that you're going to be working with. And I often found that the model fit either wouldn't converge, or if it did converge, it would be a saturated model, which can be fine, don't get me wrong, but one of the sort of difficult balancing acts you have with fitting these structural equation models with maximum likelihood is that this is a detail that I think is relevant for our discussion about Bayesian model fitting. The Lavan model tries to fit the data by optimizing the fit of the covariance matrix against the observed covariance matrix. So the problem that you have there is that you have a number of degrees of freedom to spend in your sort of model fitting routine. And you can, with these complex models, you can quickly exhaust your degrees of freedom, and you get a saturated model very quickly, which then becomes harder to sort of build on and sort of ultimately interpret. That was sort of one challenge I had, sort of just working with Lavan and working with SEMs in general. And what I kind of found to be compelling about the Bayesian approach to fitting SEM models is that the estimation routine is entirely different. You're not aiming to fit a structure or optimize your fit to the covariance structure. So you're not looking to fit against a aggregate of your observed data. You're actually looking to sort of retrodict or predict the observed values of your survey. So it's a kind of a completely different model estimation sort of approach. And it also kind of unlocks then for you the sort of more typical posterior predictive checks that you get out of the Bayesian or contemporary Bayesian modeling workflow. You can also, of course, look at the covariance structures that have been derived over through your Bayesian modeling estimation workflow, but it's not as limited in the manner in which it tries to fit data to the model. And you obviously get then the power of priors to kind of change up and down when you find like hard to fit models that where the sampler doesn't behave well. So that was the primary challenge, and like Bayesian approaches to that model, to those complex models in general, helped overcome that challenge.
Okay, yeah. And why does using the Bayesian framework here helps? Is that a classic reason, like, well, using priors is actually helping a lot because it adds structure to the model? Or is that something else mainly?
So it adds structure to the model for sure, and you can kind of weigh in some sense where you think you have implausible values without it. It helps in that respect, but there's also kind of a detail about like once you have a saturated MLE fit for a SEM model, it's harder to then add more structure and then interpret the outcomes of that saturated model. Whereas you're not really working with the same degrees of freedom problem when you're estimating the Bayesian model, you can kind of add more structure and you get different sort of evaluation criteria that help you sort of, I think, at least to my mind, more smoothly interpret the outcomes of your model fit.
Okay, I see. That's interesting. And how was using PyMC for that kind of model? Because I don't think when people pick up PyMC, they think about these kind of models. Maybe causal inference, they pick it up for that, but to do SEM or CFA, I'm not sure this is something that's a software that pops into people's mind easily. So can you discuss how you used PyMC in this tutorial and what advantages did you see that PyMC provided when modeling complex structures like those in your SEM and CFA tutorial?
Yeah, so like I'm not... I'm very impressed with the sort of flexibility of probabilistic programming languages in general. And I think even under the hood, Blavan, for instance, fits the complex models using Stan, right? Like it's maybe not the historic natural fit for fitting these models. I don't know enough about the history of psychometrics, but I think there have been a couple of recent books from like 2021 and 2020 on Bayesian psychometrics or Bayesian structural equation modeling that have been released, and I would be kind of maybe hopeful that there'll be more Bayesian structural equation modeling done in the future. I think these models are sort of inherently complicated to articulate, and with the reason why packages like Lavaan and I guess Blavan and I think Lizrel and all of these things were sort of used widely is because it hides a lot of the complexity behind a nice, cleaner UI. And like it's a validated UI in some sense, right? So these model fit routines have been well justified, battle tested, and like you don't want to be using necessarily a sort of bespoke tool for the complexity that accrues to these types of modeling routines. I use PyMC because I'm very familiar with PyMC. These models are sort of inherently probabilistic, so I think it is a natural fit for expressing these types of structures. But because of the complexity of these models, if you were working in industry or if you were working in academia and you don't want to build these models by hand, you should probably use like a package that sort of is more battle tested for SEM modeling than PyMC. That's not to say we, couldn't invite an alternative to Blavan but on a PyMC base, but like it would be a lot of work, and I think like perhaps redundant.
I see. Okay. Yeah. But still, yeah, to me, that's amazing to know that if you're already comfortable with Stan or PyMC, you can write up these kind of models in this framework. That's really cool. And that's why I really encourage people to take a look at your tutorial, because, the code is in there. And so that's, at least to me, that's really how I really understand the methods, much more by reading the code, much more than by reading the equations and what the model is supposed to do. When I see the code, it really helps usually to understand what we're trying to do.
Yeah, 100%. Again, that was part of the appeal for me, to learn the nature of the model, was to see if I could build it. And I was pleasantly surprised to see that I could.
Yeah. And how do you go about, developing? We talked about that, but a question I often get, and myself also I get in my work with the Marlins, it's, how do you validate the models, right? What criteria do you use to assess model fit, model accuracy, to understand whether going a more complex road would pay off or not? Because often developing a model is a lot of choices, right? It's a bit like a garden of forking path, right? Where, you can always come up with a more complex method and model, but it's going to take time and resources, and that's an opportunity cost for you as the modeler, and then of course the company. So how do you think about these topics? How do you decide on that? When do you think that adding complexity is worth it or not?
Yeah, so these are good questions. Maybe I think there's probably two parts to this at least. So there's just questions of sort of evaluating model fit in general, and for a SEM or a CFA model, it breaks into at least two sort of views on the problem. One is sort of measures of global model fit. So this is where you try to look at the model as a whole and find one summary statistic that is your measure of performance. Like this kind of lens is like maybe in typical regression, maybe someone overweights the importance of R squared as a measure of performance, right? There is analogous summary statistics used in sort of traditional SEM models, a ton of them actually. They're sort of like indices of global model fit. And then there are also measures of local model fit. So, and what I mean there is, like, instead of looking at the overall model, you look at how well does the model recapture sort of relationships. So imagine your model has a covariance matrix of like kind of 5 by 5 or something like that, right? Where you're interested in particular the covariances between the outcome of interest and one of the main drivers in your joint distribution. And you're primarily interested in preserving a good model fit to that relationship. Then you can look at sort of how well your model recovers the covariance or the correlations between that component of your overall covariance matrix after your model has been fit. So in that way, you can distinguish model evaluation criteria to be local model evaluation criteria or global model evaluation criteria. And so in the tutorial, I tried to pull out kind of two views on this, like because it's a Bayesian model, first of all, you can do posterior predictive checks in general. So you can do posterior predictive checks across this multivariate distribution, right? So across the 15 or so input variables, how well am I retrodicting all of those variables after the model has fit? You can also then sort of aggregate up the relationships and sort of build a predicted covariance relationship between each of those output or outcome variables, and then compare that to the observed covariance relationship in your sample. So you can measure how well your model recaptures the observed covariances you can also measure how well your model captures the observed data points. And you can then also do like kind of LU or WAIC measures on the outcome in general. And that falls into sort of the typical Bayesian posterior predictive checking sort of routines. So there's kind of multiple lenses on how you evaluate the model, just based purely, say, on a statistical metric. There's another kind of subtle thing to think about here. When you like, and this goes back to the fact that confirmatory factor analysis and structural equation models are sort of articulations of a theory that you want to evaluate. So like, if your theory is about a dependency relationship between, say, parental support and life satisfaction, and you have this mediating structure between like whatever other variables that you're interested in, you want to answer questions about that dependency relationship, right? So articulating the right SEM structure or the model structure to be able to interrogate those questions in itself will kind of lead you to build a particular model structure, right? That could be compared to a less complex structure, but the less complex structure won't be able to answer that question that you have in mind. So like, even though you might then look at these two models on the aggregate statistics of fit, and maybe the less complex model does better, but it fails to answer the question you're interested in. And so then when you're weighing up your resources and your time allocation or whatever, like, you build a model that answers the question of interest to you, whether that's like the best fitting model or not. This is the closest articulation you can get to your theory, your theoretical question, which presumably is important because it's going to drive a decision for you in work or you know, in your day to day. So yeah, there's multiple dimensions on which to evaluate fit and complexity trade-offs, but the psychometric discipline seems to be focused on trying to answer the theoretical question that matters, right? So like,
yeah, that makes sense, and that's also usually what I answer people when they ask me about that. That it's more, you have to look at a collection of metrics and comparison much more than just looking at one of them and call it a day. Because
yes, that's true. I actually also, another element, sorry, no, this is complicated. Another element of evaluating these models, especially in the Bayesian setting, is the real and vital importance of sensitivity checking. Like sensitivity checking to how you set those priors, right? Like if you have articulated the model you want, it has the right structure, you really need to make sure that you're not like skewing the thing by having too loose a prior. So like, as part of this workflow with a SEM model, at least you want to be damn sure you've done good sensitivity analysis to make sure that the results that you're interested in hold even after like changing reasonable priors.
Yeah, that makes sense. That makes sense for sure. And that's related to simulation-based calibration, I guess. So that's also something I really recommend more and more if you have computing power or a model that's not too long to fit, or if you can use amortized Bayesian inference, is doing simulation-based calibration even before fitting the model to real data. That's really good, because that gives you confidence that the model is doing what you want it to do. So once you start hitting roadblocks, when you start fitting the model to real data, you know it comes either from a model structure or parameterization issue, but at least it's not coming from the DAG, if you want, that you had in mind, because you know that if the DAG you have in mind corresponds to the data you observe, then you'll be able to recover the parameters. So we recommend doing that also. And could you, like, actually talking about difficulties and roadblocks, are there any technical insights or interesting findings from writing your tutorials that were particularly striking or unexpected to you?
I mean, the thing that tripped me up most when building these models probably is I started with this confirmatory factor baseline kind of model, which is, I think, it is also called the measurement model, right? So before you add extra structure amongst the variables, you want to get just establish the relationships between your observed data and the factors of interest. So that building that went reasonably smoothly. The thing that tripped me up when I was trying to add structure onto that was like I initially just added regression formulas effectively into the PyMC model context, and it wasn't working. And I realized at some point it was because I had just like fixed formulas. I wasn't sampling those kind of latent structural formulas. I wasn't putting them in as a random variable. It was, so instead the formula had to be put inside a sort of a normal distribution as the sort of the mu parameter. Like we're predicting the center of a normal distribution, and then the model gets to sample the rest of the random variation associated with that regression equation. And like I had been too optimistic in guessing that the fixed formula would be enough. Rather, there's also variation or random variation that needs to be accounted for as you build these, as you build the structural components of your SEM model. The regression equations themselves are sort of probabilistic random variables. And secondly, when you build these regression components of your SEM model, you are taking them out of the multivariate structure that is in your simpler confirmatory factor analysis model, right? But you need to put the possibility back into the model that those regression formulas in your structure also have covariance structures. So you needed to build extra sort of residual covariance structures to ensure that if there is a sort of co-determining effect between two regression components of your structural model, that model was able to articulate that co-determination effect and estimate the degree or strength of the co-determination effect in your model. So it tripped me up getting that extra structure in there.
I see. And how did you realize it was like, how did you realize it was an issue and you had to solve it?
The model fits were worse. Like the model fits were dramatically worse. There was more divergences, sometimes utter failure to converge. Right. One of the maybe surprising things is like the model structure there in PyMC converges really fast for such a complex model. It takes like 5 minutes to fit that data. So it wasn't working cleanly. So that was, you could see that in the model fit statistics, but you could also see it in the sort of health diagnostics of the sampler, which is kind of that's a nice aspect of HMC. In some sense, it's like, if it's not working, it's also an indication that your model is poorly specified, right? So
yeah. I mean, divergences are really, the nerdy realization of the idea that the obstacle is the way. It's always terrible to see the divergences, but in the end, they're always a blessing. But it really costs, adapting your mindset to be like, oh, that's great, I have divergences, instead of being like, oh my god, no. So
yeah. There was some banging of my head against the wall as we tried to figure out.
Actually, so we mentioned SEM, CFA, we mentioned causal inference, but we didn't explain yet how these methods intersect together. So can you explain the role SEM and CFA play in understanding causal relationships in data?
So I mean, there's actually a nice paper, Judea Pearl and I think Ken Boland, and it talks about the nature of the relationship between structural equation modeling and causal inference. The sort of argument there is that, like, it goes back to the fact that these models are articulations of theory, like they're articulations of a relationship that you think holds between, like, whether it's constructs or independent metrics or not. You're sort of building a theory that you ultimately want to believe is causal in some sense or other, in most cases. It doesn't give you causation for free. You still need to put the right variables in the model, structure them appropriately, make sure that you try to remove as much confounding as possible. And in some sense, factor analysis, the fact that you're collecting a bunch of metrics underneath one factor helps you articulate or disentangle the independence relationships between multiple data points and recover like conditional independence structures, which will give you license to make causal claims about your model if it's well fit. But the discipline is sort of inherently about articulating a claim about the effects of the relationships between these variables. So it's kind of inherently causally keyed, if you get me. Yeah.
I see. Okay, that's interesting. And so here that's interesting to me to hear that the factor analysis is helping actually in these causal, like recovering the causal relationships, because intuitively I would say that it could muddy the waters because you're reducing the dimensionality of your data, which I really get why you would do that, but I would have intuited that would make causal inference harder.
There's a nice quote at the end of the tutorial I have from Jude Pearl there, where it's like you're using these factor-like structures to potentially create a new construct, but that could be like doctors can just create a new syndrome based on different aspects of behavior or sort of, health response that is hard to sort of think about when it's this sort of multivariate presentation, like 10 different symptoms. You want to call those 10 different symptoms, group them together, call it a syndrome or something like that, which helps you then think about the structure between outcomes. And so rather than having to work out what's the outcome, like do they live, die, or, suffer in pain for 10 years due to this presentation of 10 symptoms, it's like, what is the probability of survival based on having this particular syndrome, right? So it's this sort of, it's not only is it a dimensional reduction technique, it's also sort of a theory refinement technique, right? Because you have lots of data around things which are potentially presenting in a very complex way. By gathering them under a factor, you sort of unify, make more elegant or clean your theory in a way that you hope to be justified theoretically. Like, it's not just like there's work to be done to make a SEM model a compelling causal account of the relationships between these variables. So it's not for free, but like the structure lends itself to building a theory about what drives what causes what. And so that's how you can use it to articulate the complexity of those relationships.
Okay, fascinating. Damn. And do you have some practical applications in mind of these methods in real world scenarios, especially when it comes to understanding risk and causal inference?
I kind of want to use these ultimately to look at sort of employee engagement type survey data. Mm-hmm. So I want to know what are the sort of themes that are driving the successful outcomes for an engaged workforce, for instance, based on their responses across clusters of thematically grouped questions. So those questions might be related to their worker autonomy in their role. It might be related to the working conditions of the job. It might be related to their view of the company writ large. Like, what are the decisive factors that have more sway in influencing the outcome, which is like a score of employee engagement? And I think more generally, just across well-designed surveys will give you clusters of questions which are sort of mapped to appropriate themes, which can be kind of articulate it as a factor analysis model, and then you want to kind of figure out what is the sort of relationship between, the employee's sense of autonomy and their sense of engagement. Right? Like you're not going to ever measure autonomy directly, but you might measure it indirectly via a well-designed survey. And I think similar use cases are done across the social sciences. Like these models are sort of built in such a way that they can take these complex presentation of multivariate survey responses and sort of thematically group or cluster these responses in ways that allow you to better articulate the theory of what's going on behind the scenes.
Okay. Yeah. Okay. I see. So a lot of survey data, basically. That makes sense.
I think survey data is the use case I kind of have in mind, but I think there's applications beyond that as well. It's like any sort of complicated mess of measurements that you want to sort of add structure to make more compelling an account.
Yeah, that makes sense. Something I really like. So I said it in the introduction to this episode that you have a background in philosophy and mathematical logic, which I find super interesting and very original for that field. So I'm wondering, how do you see these disciplines influencing your approach to data science and probabilistic modeling?
I think deeply important to the way I think about these problems. Maybe like philosophy in general, I think is a fascinating study and more people should do it. But the probably more direct influence is the sort of study of logic that I did. So a lot of the focus of when you're studying a logic or various logics is the way you want to express different consequences or different inferences between your assumptions and between your assumptions and the predicted outcomes in some sense or other. You have varieties of logic that encode different consequence relationships. So there's relevance logics, there's justification logics, there's dynamic epistemic logics. There's a whole range of these particular things, and they're all kind of just different little lexicons with different connectors and rules of consequence. So how you can derive a conclusion from a set of assumptions when you're working with a relevance logic versus when you're working with classical logic are different. They have different sets of consequences. And what I kind of found when I was working with those things is there is a sort of there are natural arguments you want to make or inferences you want to make which are blocked when you're using a particular logic. And what I find fascinating about sort of PyMC and probabilistic programming languages, it's also a language. You get to articulate different structures and draw inferences in ways that are sort of mathematically defined and structured. But it also lets you answer questions which are fuzzier than, does this follow necessarily from your assumptions? It's this follows probabilistically with some degree of surety here and there. So I think the focus on logic, the structuring of your argument in that also leads me to think about modeling as structuring an argument in some sense. Every model you build, to my mind, is like an argument about the state of the world. You are saying the world is thus and so, and here's how I'm measuring that, and here's how I'm evaluating that claim, and I'm retrodicting against past data to sort of reinforce that my model is a good fit to the world. It's an argument about how the world is or approximates, how we can approximate the world through this linguistic structure. So yeah, I don't know if that answers your question exactly, but
yeah. No, for sure. And also something I've seen you talk about and express is keen interest in inference and measurement in the presence of natural variation and confounding. How does this interest of yours shape the way you design your models?
Yeah, so that's kind of so I think maybe I just have a very suspicious personality, and that I kind of think that the world is constantly trying to fool me, or that there will be a confounding relationship in the data that I'm working with. And that's kind of generally led me to look at the sort of causal inference questions. And so causal inference can be just considered like a collection of methods or models that attempt to adjust for suspected patterns of confounding in your data generating processes. A nice kind of overlap between the SEM world and the sort of causal inference type models is the Bayesian formulation of instrumental variable designs. The Bayesian formulation of that model fits a multivariate normal distribution on your treatment and your instrumental variable, because you want to measure the sort of correlation and covariance between those two things to adjust for the confounding relationship, the confounding influence of a third variable on your treatment data. Right? So that is kind of like the instrumental variables and path tracing rules. They were all of them were like first envisioned or imagined by Sewell Wright, who came up with like a lot of these SEM structures and instrumental variable designs. And both are kind of like attempts to articulate a model structure that adjusts for, the risk of confounding in your data generating processes. And I find that like species of like this way of looking at the world, that like there is a data generating process. There is a risk of confounding if you think your data generating process looks anything like this. And here's a technique or a sophisticated like adjustment you can make to your model to account for that. So that sort of sits at the heart of the way I think about modeling. What do I need to adjust for? Where are the risks that this is going to go completely wrong? How do I sort of validate that I haven't gotten it completely wrong?
Yeah, with the advancements that we see now in generative AI, I'm curious, what future trends do you anticipate or maybe hope for in the field of causal inference and structural equation modeling?
With the specifically with respect to the advancement of generative AI.
Or just what future trends do you see in general in these fields, and maybe things that you hope for?
I think the causal inference, I feel like, has been getting a lot of traction, like the importance of confounding in basic like data analysis, even just like that is more and more visible, like even in even just in industry, like the prevalence of sort of quasi experimental designs. To like, maybe you're working in industry and people don't want to run an A/B test for everything, but they're just launching a new policy, a new procedure, and they want some sort of guide on how to understand what the impact of that policy is. The proliferation and spread of understanding of causal inference and confounding risk for the evaluation of those new policies or procedures, I think has gained a lot of traction in recent years, and I would hope it continues to do so. And with that, the increased understanding of risk of bias, waste due to biased conclusions, increased caution, like I think like the poor causal inference is a kind of zero interest rate phenomenon, right? Like if money's on the table and you're going to waste money by doing something really poorly, you want to do that inference well. And so now we're not quite in a zero. I know the interest rates came down recently in Europe, but we're not back to zero interest rate world yet. So I'd expect causal inference to go from strength to strength over the next couple of years.
Yeah, I see. And if you also, I'm wondering if you have advice that you would give to aspiring data scientists interested in specializing in what you're doing, which is, the intersection of probabilistic modeling and causal inference.
I think it's generally always just like if you're like really young and you're on the job market and you're looking for like a sort of portfolio piece or something like that, always find a problem that you're interested in, like not one that exists out there, like a niche data set. Maybe you create your own data set, kind of show the workflow and the thought that went into your understanding of the data generating process, and that you can think about the aspects of that data generating process which would support your conclusions but also threaten the conclusions. And the ability to be able to articulate that understanding is more important to me when I'm like hiring than the ability to say you just deployed the latest fancy model. I just want to hear that you've thought about what is the thing you're actually measuring, can think through the problem in some sense or other. I think that's more impressive on the job market for a new grad than it is to say that you have played with the latest deep learning phenomenon.
Yeah. Because I think this also shows that you're able to learn, and I think that's one of the most important things in our jobs, because I think one of the best job descriptions of our line of work is the ability to be uncomfortable all the time, with what you think and being able to always update what you're doing, how you're doing, and why you're doing it. Extremely important. Completely agree with you.
Yes, I would also emphasize like good communication is going to be vital in any career.
Right. Yeah. That's true. Yeah. Ability to communicate complex topics to different audiences and break them down is extremely important. Yeah. So that's why also, making the effort to do the communication you're doing with your written articles and also coming on the podcast, different media, that's really part of the job, I would say, not something that you do, on the side, because what counts is only the code. Because good code that's not used is not very useful.
Yeah, utterly useless, yeah.
So to close us out, before I ask you the last two questions, are there any future project or research areas that you're currently excited about, particularly involving Bayesian methods, of course, but things that you're learning right now that you're really excited about?
I'm kind of focused on two things at the moment. More and more into sort of synthetic control methods for causal inference. And I kind of want to go back to basics a little bit on understanding just survey methodology and how to think about surveys well, especially stratified survey sampling. So that's kind of on my radar to do.
Should we expect a new in-depth tutorial about that?
Yeah, probably, but like a couple of months down the line, I think. Yeah.
Sounds good. Yeah, can't wait to read that. Well, Nathaniel, that was really a pleasure to have you on the show. I think we were able to cover a lot of ground, so thank you so much for taking the time. Of course, before letting you go, I'm going to ask you the last two questions I ask every guest at the end of the show. So first one, if you had unlimited time and resources, which problem would you try to solve?
So I had a kind of idea for this, and I'm not entirely sure how I'd go about it, but like, I feel like there's like this general tragedy of the commons kind of phenomena that you like have, say, for climate activism or for even just like working effectively in a big organization with politics and little kind of kingdoms being built here, there, and everywhere. I'd love to know, like, for different organizational structures, how do you mitigate, if not solve, these sort of risks for tragedy of the commons? Like, so for more efficient more efficient workflows for an organization that can mitigate the risks of sort of tragedy of the commons effects.
Yeah.
So like if infinite time and money and like a big research proposal, probably fine. For different organization structures, there's different mitigation strategies, and then which ones to apply where and how, that kind of thing.
Yeah. Definitely understand that. That's great answer. And second question, if you could have dinner with any great scientific mind, dead, alive, or fictional, who would it be?
Yeah, so I was thinking about this one. So like, is it a hard requirement that it be a scientific mind? Because I was thinking like it would be great to have dinner with Borges, the Argentinian short story writer. He wrote beautifully concise short stories. But if a scientific mind is a hard requirement, I think I would go for the sort of philosopher Nelson Goodman.
Okay, yeah, both good choices. I will allow José Luis Borges because he's Argentinian and my wife is Argentinian, so definitely I have to accept him. And also, definitely, I love that choice. Both are. I think for both choices, it's a first on the show. But I love both, and I would argue also Borges influenced quite a lot of scientists, right? So I think he was the one who wrote The Garden of Forking Path. I think one of the stories is called that. So you could argue it's almost a scientific story.
I think so. Also, Library of Babel is like this excellent little mediation on combinatorics in a short story form. So,
nice. Yeah. Well, so definitely awesome. Well, that was really a pleasure, Nathaniel. As usual, I'll put resources and a link to your website and socials and the papers and of course your tutorial in the show notes for those who want to dig deeper. Thank you again, Nathaniel, for taking the time and being on this show.
Thank you, Alex. It was great.
This has been another episode of Learning Bayesian Statistics. Be sure to rate, review, and follow the show on your favorite podcatcher, and visit learnbasedstats.com for more resources about today's topics, as well as access to more episodes to help you reach true Bayesian state of mind. That's learnbasedstats.com. Our theme music is Good Bayesian by Baba Brinkman, feat. MC Lars and Megaran. Check out his awesome work at bababrinkman.com. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. You can support the show and unlock exclusive benefits by visiting patreon.com/learnbasedstats. Thank you so much for listening and for your support. You're truly a
good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. Let me show you how to be a good Bayesian. Change calculations after taking fresh data in. Those predictions that your brain is making, let's get them on a solid foundation.